Hello, welcome back. In this video, we'll discuss the Davisson and Germer experiment. From the de Broglie's hypothesis, we know that matter behaves like waves. But the hypothesis was not tested experimentally until the Davisson and Germer's experiment. The Davisson-Germer's experiment essentially gave us the experimental proof for the existence of matter waves. These are the two gentlemen, Davisson and Germer. They have conducted an experiment in 1927 to show that electrons also behave like waves. One of the basic characteristics of a wave is to exhibit interference and diffraction under suitable conditions. Since electrons are also matter waves, they should also exhibit the interference and diffraction patterns under suitable conditions. This is the basic foundation for the Davisson-Germer's experiment. The experimental setup is given here. Since we are experimenting with the electrons, there should be a source of electrons. So we have an electron gun. This is the electron gun. It will have a filament. When the filament is heated, one can get the electrons from the heated filament. In total, this small equipment is called as the electron gun. The electrons thus emitted are made to propagate through an accelerating anode. The anode is used here because we want to increase the kinetic energy of the electrons. Thereby, one can reduce the wavelength of the electrons. So we have an electron gun and an accelerating anode. This anode does two things. Firstly, it increases the kinetic energy. Further, it collimates the electron beam. And these electrons that are accelerated were made to hit a nickel target. The target is a nickel crystal. In order to measure the diffracted electron beam, we'll have a detector here on a movable scale, on a semicircular scale. All those electrons diffracted in any particular direction can be measured using a movable detector, and we have the diffracted electron beam in this direction. Since we are using the electrons, the entire chamber is evacuated. Reason is to avoid the interaction of the electrons with the air molecules, we evacuate the chamber, so we'll have a vacuum chamber. The entire setup is enclosed in a vacuum chamber. This is the power source for the anode. This is the power source for the heating element. The crystal is mounted on a rotating table so that its orientation can be adjusted. Top view of the arrangement looks like this. We have a nickel crystal here. We have the detector there. We have the filament that generates the electrons. The electrons are made to propagate through the anode, and from there they fall on the nickel crystal. After undergoing diffraction, they will be moving in this direction. The angle of the diffraction with respect to the incident beam can be measured using the circular scale. This is the circular scale. The number of scattered electrons moving in any particular direction can be measured using the detector. This detector is connected to a galvanometer. When the filament is heated, electrons are produced, made to propagate through the anode to achieve high energetic collimated beam of electrons. These electrons are scattered by a nickel crystal located at C. The crystal can be rotated about its axis. Detector measures the number of electrons scattered by the crystal in different directions. The detector can be moved along the circular scale. So one can measure two parameters from this. First parameter is the diffraction angle phi. Second parameter is the number of electrons moving in one particular direction. When you plot on a polar graph for an angle of 50 degrees with respect to the angle of incidence, we have a huge intensity for the electrons hitting in this direction. This is a polar graph. During this experiment, Davisson and Germer moved the detector on the circular scale to various positions. The current was measured with the help of the detector. The detector current is a measure of the intensity of the diffraction beam in that particular direction. As the accelerating potential is increased slowly, the kinetic energy changes for the electrons, similarly the wavelength. For 44 volts of accelerating potential, a bump starts in this direction, means the number of electrons hitting the target slowly increases. When the accelerated potential is increased to 54 volts, the bump increases its amplitude and reaches a maximum. When the accelerating potential is 54 volts, the electrons are scattered more in number at an angle 50 degrees with the direction of the incident beam. The maximum is an indication that electrons are being diffracted. Now we shall look at the analysis of the experimental results. In order to understand and analyze the results, we need to recollect certain concepts of physics that we have already learned. Let us try to recall the Bragg's law of diffraction. The Bragg's law of diffraction states that 2d sine theta is equal to n lambda, where n is the order of diffraction, theta is the angle of diffraction, lambda is the wavelength of the waves. The waves could be electromagnetic waves or matter waves. And d is the grating constant. What is grating constant? Grating constant is the separation between the two successive lines on a grating. We shall also recollect that from de Broglie hypothesis, the de Broglie wavelength lambda is equal to h by p, r is equal to h by mv. For an electron that is propagating through certain potential v, lambda is given by h by square root 2m where v is the potential difference through which the electrons are moving, and e is the charge on the electrons, m is the mass of the electrons, and h is the Planck's constant. In this diagram, we have the dark circles or dark dots. Each of these dots, they represent the nickel atoms, and the dashed lines connecting these dots, they represent the crystal planes. And for a beam of incident electrons, the entire crystal works as a three-dimensional grating. Interplanar spacing d is the grating constant. D is separation between successive planes of the crystal, and it is called the interplanar spacing. This interplanar spacing becomes the grating constant in a crystal like this. We have the incident beam like that hitting the planes of the crystal and undergoing reflection in this direction. Please note that we are using three different terms: diffraction, reflection, and scattering. In fact, diffraction is a special case of scattering, and in this actually the electron-electron scattering is taking place. The incident beam of electrons, they will be reflected from the crystal planes in this direction. The angle of reflection is 50 degrees or the angle of diffraction is 50 degrees, but when you measure the angle with respect to the normal drawn to the plane of the crystal, you notice that the angle is 65 degrees, because with respect to the normal, the angle of incidence is equal to the angle of reflection. But with respect to the plane of the crystal, the angle of reflection will be 65 degrees. And we know from the X-ray diffraction measurements, for nickel crystals, D is equal to 0.91 angstroms. We substitute these values. D is equal to 0.91 angstroms, theta is equal to 65 degrees in the Bragg's law, and we are assuming it is the first order diffraction, so n is equal to 1. So we get lambda is equal to 2d sine theta, which is equal to 2 into 0.91 angstroms into sine 65. So this is equal to 1.65 angstroms. So the wavelength of the electrons now measured as 1.65 angstroms. Now we shall calculate the wavelength of the electrons using the de Broglie's wavelength, which is h upon square root 2 mev. So this gives us 6.626 into 10 power minus 34 joule second upon 2 into 9.1 into 10 power minus 31 kg into 1.6 into 10 power minus 19 coulombs into the voltage that we have used is 54 volts to the power half. So after simplifying, we get this as 1.66 angstroms. This value of lambda, when calculated using the de Broglie's wavelength, is in agreement with this value. So the wavelength that we estimated from the electron diffraction experiment is almost equal to the wavelength that we calculate using the de Broglie's hypothesis. Therefore, the Davisson and Germer experiment establishes that matter also behaves like waves. The Davisson and Germer's experiment gives an experimental proof for the existence of matter waves. In this video, we have started by stating that Davisson and Germer have conducted a diffraction experiment in 1927 to verify the existence of de Broglie waves. We have seen the experimental setup and also a polar graph. We have said that the polar graph will have a maximum for a voltage which is equal to 54 volts and for an angle of diffraction which is 50 degrees. We have recollected what is Bragg's law of diffraction and also the wavelength of the electrons when made to propagate through a potential difference V. We have seen the crystal structure and we have said that the crystal behaves like a grating for wavelengths that are comparable to the interplanar spacing of the crystal. For a nickel crystal, we know that D is 0.91 angstroms from the X-ray diffraction measurements. In the electron diffraction measurements, we have calculated the wavelength which is equal to 1.65 angstroms. Using the de Broglie's wavelength, we have calculated the wavelength which is equal to 1.66 angstroms. These two are close to one another, and also the wavelength of the X-rays in the X-ray diffraction measurements giving rise to a wavelength close to 1.66 angstroms will give the first order diffraction at 65 degrees. Therefore, the Davisson and Germer experiment provides a valid evidence for the existence of matter waves. Thank you.